Sure.
Um,
Sure.
1, 2, 3. It is started.
Yep, it started. Hello, everyone. Welcome to the CES Fall 2020 Seminar Series. Today's talk is going to be presented by Dr. Ed Furlong. Now, Dr. Ed Furlong received his master's and PhD degrees in chemical oceanography, geochemistry from the University of Washington, and was a postdoctoral fellow in the School of Public and Environmental Affairs at Indiana University, working with Professor Ron Heitz. And I'll just interject here that I know he worked very hard for Ron, because during the entire time that he was a postdoc there, I was a graduate student in the same group. And so I've known Ed for well over 30 years, and he's a wonderful speaker. Ed, after leaving Ron Heitz and moving on to doing some of his own things, joined the U.S. Geological Survey, the National Water Quality Laboratory, in 1987. And since then, his research has focused on the development of state-of-the-art mass spectrometry techniques for analysis of trace organic compounds of environmental interest, including pharmaceuticals, hormones, pesticides, and their transformation products. He applies these techniques to understand the transport and fate of these compounds in aquatic and terrestrial ecosystems and the effects these compounds may have on human and ecosystem health. His research has been on an integral part of the USGS Toxic Substances Hydrology Program and its efforts to better understand the sources, transport, and transformation of emerging contaminants in aquatic and terrestrial ecosystems. In 2015 and 2016, Ed was named a highly cited researcher by the Web of Science and is a member of the Editorial Advisory Board for Environmental Sciences and Technology. Ed recently transitioned from being a full-time USGS scientist to a scientist emeritus, continuing his contributions to several ongoing research efforts. And without further ado, I'd like to introduce my friend, Ed Furlong.
Thank you, Brian. Brian, you can hear me and see my slide? My opening slide?
I can.
Okay, well, I'm assuming if you can, everyone else can. Well, first, I'd like to thank you, Brian, for inviting me to present, and that I'm really pleased to be able to be here. I wish I could be out there in Connecticut versus, doing it virtually, particularly since Colorado and much of the West is pretty smoky these days. But without further ado, I'll start my presentation, which is entitled "Still Haven't Found What You're Looking For," which is a little rock song allusion here. We talk interdisciplinary analyses may be the solution. And my primary co-authors here are Susan Glassmeyer, also a former Ron Heitz graduate student who I've worked with for a long time she's at the U.S. Environmental Protection Agency in Cincinnati. My USGS colleague, Dana Kolpin, also with the USGS, but in Iowa City in Iowa, and as well as Mark Mills is with the US EPA and is also in Cincinnati. While I mentioned the four of us, we are considered the four project principal investigators, part of a USGS, US EPA interagency agreement. Sorry, let's see what's going on here. In truth, the project is a lot larger than that. And just highlight my colleague Dana, Susan, who I've been working with on this project for almost 18 years now, Mark Mills, and then myself. But in reality, you can see there's about 25 additional researchers from USGS, US EPA, and in academia, all who have contributed in one way or another to the discussion that we're going to have today. And they're scattered across the country, as you can see here in this little map. But before I go much further, I have to put up our disclaimer, which these days seems to get bigger and bigger and bigger. But basically, I'm saying, that anything I present does not necessarily represent the views of policies of the USGS or the US EPA. There's no endorsement of anybody or anything or any products, services, or enterprises. Information is subject to revision potentially, as it is preliminary, and it's being provided to meet the need for timely best science. and we won't be held liable for anything from our authorized or unauthorized use of this information. This has probably doubled in the last decade. So I apologize in a sense for that, but without further ado, as I said, the USGS and the US EPA have been operating under the auspices of an interagency agreement, which tries to leverage resources from both our agencies for providing timely, objective science that has use and value for water users and managers. And like many of us, we are been using as a paradigm the water cycle. And this is a little cartoon that Susan has put together. And I think we all understand when we try to talk about talk about contaminants of emerging concern, they have diverse sources, our medicines, products we use like cigarettes and nicotine, consumer products that contain caffeine, such as coffee and colas, and a wide variety of other personal care products and household cleaners, etc. Those end up in the wastewater system, are discharged and enter into the system. And then for much of the United States, many of those discharges are upstream of water sources that are then treated and used for drinking water. And so there's a real interest in how our actions and interactions of all these products going into the wastewater system, being discharged and then being taken up, are affecting water quality and their potential for exposure, first for humans through drinking water, but also downstream where ecosystem health can be affected. So while a major focus for EPA in particular in this project has been human exposure through drinking water, it's not been exclusively that. And this project has been very productive. This is a series of papers we published in between 2017 and 2019 on just one large multi-year study looking at drinking water, which I'll discuss briefly here as an example of what we've done. But we've also looked at the effect of contaminants of emerging concern and recreational water quality, the relationship to microbial indicators of exposure and recreational water, such as beaches, so our potential exposure that way. But it's been a highly productive collaboration. One of our biggest projects, as I've said, has been this national scale drinking water study. And you can see in this picture, we looked at samples from all the EPA regions. They represented we looked at drinking water sites, and we looked at source and treated water using all different kinds of drinking water treatments, different population sizes as indicated by these bars, and multiple sites within each of these regions. So we were trying to be representatives. The numbers indicate the number of sites within each region. So some regions got a little more coverage than others, but we had about 25 sites ultimately. We did do this anonymously because at the time we started this study, there was a lot of concern within the drinking water community that since these compounds were not being regulated, would they be then exposing themselves to a public perception that they couldn't really answer with the tools and techniques that they've been held to under regulation for drinking water quality. So it was very great. It was great that these drinking water treatment plant operators were willing to step up and work with us. But as part of the whole agreement, we kept them anonymous, since nobody ever wants to be first in case something hits the fan, as it were. So that kind of gives you a brief description of that study that produced all those papers. And we looked at a lot of chemicals. We looked at over 112 pharmaceuticals, and both prescription, non-prescription, some of the metabolites, hormones, trace elements, PFAS, but we didn't simply focus on chemicals. We also looked at industrial chemical fragrances, legacy compounds like PAHs, surfactants related to detergents, pesticides, some other basic household chemicals, as well as plant and animal sterols and phosphate that are derived naturally, phosphate-based flame retardants. But we also looked at organisms, microorganisms that are of potential human health concern. So we felt at the time that we had done a pretty comprehensive study of these different compounds that could be present in source and carried through into treated drinking water, so we could understand the potential for exposure, primarily for humans, but also for ecosystems. And we looked at, for example, the occurrence or frequency of occurrence in terms of number of detections shown here. And we saw that, for example, pharmaceuticals were much more frequently detected in some of the plants, which are indicated by number here, DWTP4, for example, 3, whereas some other compounds would be detected fairly uniformly, such as the perfluoroalkyl substances, the PFASs, were detected in source and in treated water. The light bar is source water, the dark bar is treated. We also looked at some other anthropogenically derived waste indicators, things like benzophenone, those phosphate flame retardants, base flame retardant, and some of those fragrances, AHDN and HHCB are commonly talked about, as well as our inorganic chemicals, which are predominantly, but not necessarily totally, derived from source water geochemistry, as well as microorganisms. And I apologize, I didn't mean to switch so fast, but this is some of the things we saw in source water. You can see the pharmaceuticals, sulfamethoxazole. We include lithium as a pharmaceutical because one of its major sources to drinking source water is from its use as lithium carbonate used in dealing with some neurological conditions, carbamazepine, an anti-epileptic, and a number of other fairly commonly used prescription and non-prescription drugs. The very commonly used caffeine, for example. Again, some of these anthropogenic waste indicators, triclocarbon and triclosan, which are in a lot of disinfecting soaps, for example. We're seeing them used quite a bit now during the pandemic. Triazoles, and corrosion inhibitors, DEET, the insecticide, but also pesticides like atrazine and metolachlor. Depending on where you are in the country, those can be quite significant. A number of inorganic chemicals, as well as some of these microorganisms. And we found that overall about 148 out of the 247 compounds or elements were detected at least once in source water. Then when we go and compare that on a national scale to drinking water, we see there's a lot less. A good thing, obviously. Lithium is present. It just moves conservatively through from source to treated water. And we had some low detections of metoprolol and a few other of those anthropogenic waste indicators, including atrazine. PFAS, as I mentioned earlier, were fairly minimally removed from source to treated, regardless of treatment. And a number of the inorganics, as I said, are probably a function of what's in the source water, maybe with the exception of nitrate, which can be contributed from agriculture or land application of fertilizers. But the good news is we didn't detect any microorganisms, so we know at least microbial water quality is being maintained during the treatment process. And again, about 121 different compounds or elements were detected at least once. These are the commonly detected ones in this list here. And this table shows you some of those by class. So for example, the pharmaceuticals in source versus treated have a much, when broken out a bit, they have much higher some concentrations in a few plants that we saw. Others not so much. The perfluorochemicals, which we detected quite often, had fairly variable concentrations. Same with some of the anthropogenic wastewater indicators and some of the elements. And again, more often in source water than in treated water. And the minor elements, most of which are from the lithology of the source water drainage basin, you can see they stay fairly conservative and move through. We're even able to understand when we broke down and looked at some of the PFAS compounds that in cases of some treatment processes that used fairly large granular activated carbon beds. This one was almost 12 feet, fairly long contact time and fairly actively changed on almost twice a year. We saw that there could be substantial removals of some of the PFAS, but primarily by sorption to that graphitized active carbon. In contrast, we would look at others where the bed was narrower and the recharge rate was longer. You could see there was less of a removal, and others still where the bed was small but the recharge rate was even longer, you might get minimal removal. So we published this in 2019 in Science of the Total Environment as one of those papers. We're even able to identify PFAS signatures related to different rivers, so in different inputs based on different perfluoro PFAS, perfluoro butyl pentyl acids and the sulfonates, the hexyl, the octyl sulfonates. We could distinguish those being transported, and these are in two different large river systems in the east that were within our sampling. So these are the source waters, and you could see they had distinct patterns. And these three plants up here, DWTP 12, 2, and 21, span the distance of more than 1,000 kilometers. Similarly for large river B, so they had very different sources of PFAS to their the large river systems, and they were staying pretty consistent in the source. And then some other profiles were quite variable, indicating that they had different sources, and we did not have subsequent downstream plants to compare. So we learned a lot from this study. In addition, we took some of that information. We were able to work with our colleagues, Jocelyn Rice and Paul Westerhoff. Jocelyn was at Arizona as a graduate student with Paul and has since moved on to an academic position. We're able to use their de facto reuse model, which is an ArcGIS watershed model, and we could ground truth their model using some of our contaminants. Prior to this, they had used volumes of discharges, intakes, and their locations, and I'd estimate the unintentional but unavoidable fractions of wastewater that enter drinking water sources. By applying the model using our chemical data, where they were able to look at that and identified percentage reuse that they calculated, which varied anywhere from 0.01 to better than 10%. And we could look at the chemical detections in the different plants and these different water streams. Stream water refers to size. And we published this in 2018 for 22 surface water drinking plants out of our set in our phase 2 study. And we looked at quantitative detections for all organic pharmaceuticals and anthropogenic waste indicators. And by summing those, with the exception of one outlier, we were able to come up with a fairly decent correlation that showed that for most of our sites, that de facto reuse varied somewhere between 0 and 8 to 10%, which worked pretty well with most of the detections here. So with estimates from the model here. So we felt like we'd done a decent job of using this data to extend our chemical information to some water management questions. So we felt like, well, we know a lot, but perhaps we might be like within the parable of the blind man. I think we all are familiar with this idea that blind men, or in this case, blind scientists, keep coming up and touching an elephant, and depending on what they touch, they might think it's a snake or a tree or a wall. This is a fairly hoary old analogy, but I think it has some application to how we study and understand water quality. For example, if we were just using targeted grab sample and getting snapshots of concentration, we would have one perspective of water quality. Again, we see this when we do and use and compare it to data from studies that use integrating samplers, passive samplers. And if one is using targeted analyses and grab samples, one might get very different results if they use non-targeted analyses, which gives us presence of in some cases, astounding number of chemicals, or at least molecular signatures of chemicals in the environment. And another means by understanding what's affecting water quality is to look at the effects of contaminants which are inherently in mixtures, by applying bioassays to see how those bioassays, which are potentially negative responses at the organismal or at the cellular level, how they might respond to water which contain these contaminant mixtures. So what we tried to do is to look a bit more comprehensively at this study. In addition to the grab samples that we had done in our big study, we decided to focus down, and we went and collaborated with one very cooperative drinking water treatment plant to do a much more extensive in-stream study of source water that occurs, the source water that came to this plant, as well as looking upstream, approximately 10-kilometer stream reach above a wastewater treatment plant discharge, looked at the effluent itself, looked in the mixing zone immediately downstream, and further downstream, using a Lagrangian approach to effectively follow water quality as it moves downstream. And on top of that, we used integrative passive samplers, which were deployed. Unfortunately, we weren't able to deploy at all 6 sites, but we were able to deploy at 4 sites upstream in the mixing zone downstream, so substantially influenced by the wastewater discharge, at the drinking water treatment plant intake, and then within the plant. And we just looked at this one approximately 10-kilometer stream reach. We sampled it multiple times in October of 2014, April 2015, and August 2015, and we had these 4 to 6 sampling points. So we felt like we had a fairly comprehensive sampling design, as well as we were going to look at chemicals, microorganisms, and bioactivity. And within chemicals, we were looking both at targeted chemicals similar to what we've looked at prior to this individual study, looking at that large national scale study. We went on to add in non-targeted. So again, trying to go back and understand water quality in light of the samples that we started, in light of the paradigm of the elephant, and trying to back away and maybe see more of the elephant. Well, to move on, I wanted to say that a little bit about the 2 utilities within the water stream reach. And the wastewater treatment plant discharges approximately 1.2 million gallons per day, serves 1,700 people, and uses advanced secondary treatment with UV disinfection. This is representative of the majority of wastewater treatment plants across the United States these days. And the drinking water treatment plant serves a larger population, and the intake is approximately 4.5 million gallons a day of water. So you can see that the discharge upstream could be a substantial fraction of the source water intake. As I said, it serves a larger population, about 37,000, and uses ozone, flocculation, sedimentation, graphitized active carbon, which we talked about earlier, and sand filtration, the initial ozonization, and then finally treatment with chloramination. Should note that ozone was added to the treatment water disinfection train after our first round of sampling. So some of the differences we might be due to that, but wanted to mention that. These plants are continually monitoring and improving their treatment, both due to regulation and also to try to improve processes to meet regulatory requirements. So this change during the sampling campaign is not surprising if it was unexpected. And as I mentioned earlier, we use discrete sampling up at all 6 sites. We used at the upstream, effluent mixing zone, and downstream. We had a sampling device that we deployed approximately 2 feet below surface, so we're getting surface water. This was a fairly shallow, small river, and filling our bottles. At the effluent, we simply grab the bottle, placed directly into the effluent pipe stream. At the drinking water intake and treated drinking water samples, we're able to collect samples within the plant because they had their own sampling taps within the plant. So that covers those were all grab samples. And you can see here this within stream sampling, and down here you can see the collection within the effluent pipe. Water was then immediately decanted into individual sample bottles and transported overnight using FedEx or UPS to get them to the various laboratories that were analyzing them. One method, the one that my laboratory was responsible, required field filtration, but that's a relatively rapid sample treatment process using a capsule filter and a disposable syringe. So those were done in the field and then transported overnight. So laboratories received the sample relatively quickly. And again, we were able to get a little more detail. So you can, because this was within a stream reach, you can see that within this, looking at the frequency of detections, we would see about 20% of the samples in the upstream samples, between 18 and 23% of the analytes that we were measuring were detectable in the upstream sample. And it's important to note that further upstream in this river, there are other wastewater dischargers. However, when you get to the effluent, you see it's fairly high. We see up to between 40 and 52% of compounds were detected in effluent. We were measuring were detected in effluent. Then in the effluent mixing zone, since there's a fairly substantial volume of upstream water coming in, there's a substantial discharge, but it is higher again than what's in the upstream sites. And then we see a slow but not a substantial change as we move downstream to approximately 5 kilometers. And then at the drinking water intake, we see concentrations approaching about what was in the upstream, or frequency of detection approaching what was upstream. Then we see a substantial reduction of detections of all compounds at the after treatment. Not really surprising. And for any one of these columns is somewhere between 203 to 236 analytes due to missing samples. Things happen during the sample transport process and occasionally in the laboratory, as we're all aware. And if we were to look again at break those out by organic versus inorganic, we can see those concentrations do jump up decidedly. Our frequency is fairly similar to what we saw in the prior slide. Concentrations are a little more surprising. They do jump up and then drop down fairly quickly, showing the effect of dilution. The inorganics, it's a little different. They do jump up, but not as dramatically. Certainly, the jump for organics in the first round, where we did not have ozonation as a part of the treatment train, was pretty substantial. Whereas for the inorganics, we see they're probably reflecting just natural variability here. And that jump from upstream values to the effluent point and then subsequent downstream points, they seem pretty constant, including through the treated drinking water. Should point out that Some of the round one samples were not available for inorganic analysis. We lost some of those, unfortunately. Those that I was referring to earlier. But I think you can see a fairly consistent pattern here. And if we, again, just do that by summing them, all of them, we see that same pattern here where organic observations for some concentrations is dramatic at effluent and then dropping down fairly significantly to treatment. And if we look at inorganics, again, that pattern is not quite as dramatic. And this shows a few examples of some of the compounds that we see persisting through. So we did not have PFAS data at this time, so I can't show you that. But you can see that carbamazepine goes to a pretty high concentration, as we would expect in wastewater, then with drop down through drinking water intake. And we see there's nothing present in the treated drinking water. At the time these plots were made, we only had data for two of these sets. Sucralose, which is a compound we added since we did our national scale study, and one that people recognize as being very conservative, was present. We weren't able to detect it in the effluent because of an interference problem. Then it dropped down in one of the sampling campaigns, but you can see it stays present even through treated drinking water. Sucralose is fairly inert. It's probably the most conservative anthropogenic organic chemical indicator we have that's so water soluble. Sucralose is a trichlorinated glucose, and sucralose is used as an artificial sweetener. Sulfamethoxazole, the antibiotic, again, you can see that it's pretty present here at high concentrations, then drops and kind of kicks around, but is present at low but detectable levels in a couple of sampling campaigns and the treated water. Wastewater inorganic chemicals, we see there fluoride increases and drops, and then we see it goes up in treated drinking water, but that's no surprise because it's fluorinated water. Nitrate, in most cases, removed fairly completely, although in one campaign, the second campaign, there was present in the treated drinking water. Sodium, not a surprise there. We all put sodium salt in our food, so there's a little bit of an increase in treated water, but it kind of comes down to background levels. Compound atrazine was present here in one set, which was near spring sampling, so we're not too surprised by that atrazine was being used because it's present in a lot of landscaping products and could be entering effluent in a number of ways. Iron kind of bounces around, strontium bounces around, shows sort of the variability of some of these compounds. But the point I would like to make strongly is that at this part, we might start to think we know a fair amount about this water system, correct? We've mapped it out with this comprehensive set of samples. We've looked at a lot of different kind of contaminants, but a couple of surprises came up for us. One was, for example, as I said, we were doing some bioassays, and while our estrogenic activity agreed well with what we saw on the targeted chemical analyses, it did not agree particularly well with glucocorticoid assay activity. And our colleague Elizabeth Medlock-Kakeli just recently published those in Science of the Total Environment. I'll refer you to that and be happy to provide that reference if someone's interested. But and this is not an area of my expertise, but we did not come up with the kind of correlations we could see between the analytical chemistry estimated E2 equivalents versus the observed E2 equivalents bioassay. We had that a good correlation. We were not able to get a similar correlation when we looked at the glucocorticoid assay activity. So something else is going on. In addition, we also did some metabolomics work, again, looking at these data, And we found that when we looked at, we observed an increase between the drinking water intake and the downstream sample for some lipophilic extracts, which suggested contaminant input between sampling locations. That was published in 2018. Again, this is not my full area of expertise, but I'd be happy to share the publication with you. But what this suggests to us, when we look at both the hydrophilic and lipophilic results from metabolomics, and we look at glucocorticoid assays, that there may be some things we're missing simply because targeted analysis is not going to tell us the entire picture. So we took two approaches. First, we looked at our integrative samplers, and we used POSIS, polar organic chemical integrative samplers, as well as some semi-permeable membrane devices. And this morning, for you this afternoon, I'll be talking about the POSIS results. And they were deployed in those 4 locations: upstream, the effluent mixing zone, at the intake, and in treated drinking water for 30 days. Those will provide more data on intermittent or low-level contaminants, because they'll be concentrated in ways we can't concentrate the grab samples. But in addition to that, we decided to apply non-target approaches using a QTOF system, a quadrupole time-of-flight tandem mass spectrometer that we have at the National Water Quality Laboratory, which provides us with accurate mass analysis with resolution up to 50,000 and typically less than 3 ppm mass accuracy. I mention this now because I know I'm speaking to a group of analytical chemists, and this is one of the tools that has been featured prominently in a lot of literature recently, doing non-target analysis, where you look at using high-resolution mass spectrometry to look at the full scope of all ionizable compounds present in a sample. As I said, we've used a quadrupole time-of-flight system. Other people use an Orbitrap system. We used electrospray interface for polar non-volatile compounds. We have both that and the capability of using an APC-GC interface, but I'm going to focus today on the HPLC electrospray results. So first, I want to talk about what we might call one of our known knowns, which was fexofenadine, a target compound present in a number of samples that we were measuring using our direct aqueous injection triple quadrupole MSMS method. Excuse me, just needed to wet my throat here. It's the active ingredient Allegra. It's very commonly used. We detected it in the targeted method, and as I said, it was frequently detected at other wastewater sites here. And what we saw, we could get both looking at both low energy MS spectra to get a protonated molecular ion, and then fragmenting high energy spectra, we could get assignable fragments here, and we could see they were all correlated chromatographically. We could see that upstream it was present, and then its concentrations increased further, or its response, I should say, increased further as we go to the effluent mixing zone and the drinking water intake. And we even found it in finished drinking water at a concentration we were not at a response that was significantly smaller. Note that this is a log scale, but present and identifiable at the finished drinking water. And this we did not detect using our targeted method. We also noticed it was present in a field blank. One thing I should point out is that when you're measuring everything, blanks are highly important. So we had a POSIS fabrication blank as well as 2 field blanks that were part of this sampling campaign and a laboratory blank. And you'll see that in the next couple of slides. Then we had a suspect. Lamotrigine is an SSRI, a selective serotonin reuptake inhibitor. We did not look for it in our method, but we were suspected it might be present from other publications. And again, we're able to identify the high energy fragment We acquired and standardized a standard to confirm it. Here's just a spectra showing the chlorine pattern, which is reflective of the two chlorines here. We were able to look at both some high energy fragments that are indicative of its presence. And again, we saw a detection in one of the blanks, the field blank 2, as well as high concentrations upstream and in the mixing zone, and even a slightly higher in the drinking water intake, and tiny amount present in terms of response in the finished drinking water and none in the blank. So we did confirm this. It's, as I said, it's an antiepileptic, anticonvulsive, and bipolar medication. And we've subsequently added it to our routine monitoring method. Now, this was one that kind of caught us initially out of left field. It was ketamine. Again, we saw it present, not as good a fragment and at lower response, but detectable and confirmed with an authentic standard. Single chlorine present, again, a single chlorine pattern. And we were able to detect it at pretty high mass accuracy. We felt pretty good about this detection with good retention time, good minimal mass error. So, we could go on and on doing it this way, which I refer to as the peak-to-peak approach, in deference to the peak-to-peak highway, a scenic byway here in Colorado. Should you ever come out, it's a lovely drive. However, it's a highly efficient and inefficient approach. And if we're going to recognize these patterns, we want to bring in some kind of quantitative component as well. And the data challenge, which has been commonly recognized in the non-target analysis community, the environmental chemistry community, is fairly analogous to metabolomics, which has defined previously as the comprehensive qualitative and quantitative study of all the small molecules in an organism. And if we were to substitute ecosystem for organism, you might have what we might call an ecometabolomics approach. In an ecometabolomics, an organism exposed to a stressor, and we look at what's changed. We decide to apply this idea, consider the sampler kind of a passive organism, see what might be present. And so we've applied this kind of intellectual approach, this difference technology after exposure, to our POSIS data. And we're using fairly some multivariate data analyses similar to principal components analysis. So we then analyzed our samples in triplicate in the first deployment. In this example, we came up with over 3,600 exact mass retention time pairs that we could identify routinely in all these samples. Now, all you're seeing are 5 plots: what was in our blanks, what's in our treated samples, and then clustering very close together are the upstream, downstream, and source. And you saw that in the previous plots, that those were fairly similar in terms of their concentration and abundance. Now, this is a better plot of all the thousands of those different EMRT pairs. And you can see, it's good to note that there's differences between the source, water, the upstream and downstream, but they're not too far, and they all kind of cluster over here. But particularly that treated samples and blanks are not that close to each other. And if we do some additional multivariate or megavariate analyses, we can compare source and treated EMRTs in an S plot. So this is source water versus treated water. And in this plot, going in this direction, you have increasing reliability of contributions to the treated water samples until you get up here, where these are clearly unique or highly contributing to the source water or treated water samples. And conversely, the same thing happens down here for the source water. And if we particularly focus on these that are out here as increasing magnitudes of contributions to this difference from either source, let me go back, or treated water, We can then analyze these, figure out what they are, and do some using the EPA chemistry dashboard. The slide's a little dated. This number's even larger. But we look at those top SPOT candidates, treat them as putative M plus H ions, subtract a proton to produce a list of neutral monoisotopic masses, so putative chemicals, and then process them through this dashboard, which has a tool. And we can then evaluate these selections using a number of databases, the dashboard itself, Mass Bank North America, Drug Bank, the Norman Suspects database. These are large databases of accurate mass information, fragmentation information, and then down the road we'll be comparing and reassessing these using a tool called NVMass. But we're able to see some molecular formulas. Some of those we know, things like lidocaine. It shows up in a couple of different potential variants. Acetamide. Some of these others are a little unusual ones that we don't know quite yet. We're still in the process of evaluating what they might mean. But we could then go and look at these different EMRT distributions to try to understand what might be important and what might be code tracking. So we're kind of looking at the response normalized to the highest value of what these compounds might be. So here's the lidocaine EMRT, a tramadol EMRT, trimethoprim, and a fludrocortisone suspect. And you can see that they're not present in any of the field blanks. They were present at this upstream site, which is called the Old North Bridge. Then at the mixing zone, you can see they jump up to a much higher normalized concentration, and then they drop. We then looked at a few others that might even end up showing in drinking water, and some of these might be compounds that are fairly, which have been identified by others. For example, the 635 looks to be related to certain sources coming from stormwater. So it's present here. It is present in the mixing zone, but it doesn't drop that much at the intake. So there might be some other contributions. And we're seeing some of these persist right through treated drinking water. This is an area we're still very actively pursuing. And there are a few where some are highest in the upstream and are carried, are not a part of the wastewater discharge. We don't see them increasing as we get to the mixing zone. They're decreasing in some cases, and some are persisting longer, and some are persisting right through to finished drinking water. So we're exploring what these different chemical EMRT or molecular signatures might mean, and working hard to try to identify if they can be related to chemicals of interest that might be more important to our other assays. So in conclusion, I'd like to say that, based on what we've been seeing, is that de facto reuse of water can result in these wastewater derived chemicals in both drinking water source waters and in the drinking treated water. And really that targeted chemical analyses, non-targeted chemical analyses, and the bioanalytical tools like metabolomics and bioassay can each provide a unique but potentially incomplete understanding of the contaminant profile. By using these complementary sampling protocols, they provide a means for gaining greater insights to the complex chemical mixtures which are present in water, and that can be obtained individually. So we feel strongly that if you're going to be doing a sampling campaign, it's valuable to combine all of these, both the integrative samplers, the discrete point samplers, using all the targeted, non-targeted, bioassay, metabolomics, microbial indicator measurements, to really try to get a better understanding of the full scope of contaminants. And we're continuing to work to see how we can revise what we're doing. In addition, known, suspect, and unknown CECs are more frequently observed in source and treated drinking water, although at low concentrations. When we start using things like integrated samplers, passive samplers, we propose that it's likely that similar behaviors for nanomaterials, microplastic, and other CECs that we've yet to identify or measure are showing similar behaviors. And finally, and this is not a scientific conclusion, cross-agency partnerships, such as the one that USGS and the EPA have managed to maintain over 18 years, can leverage the unique capabilities of each agency to fully address drinking water questions, and hopefully are providing objective science-driven results that can inform water quality management. This is something we continue to emphasize because USGS's understanding of watersheds and water movement, working with EPA and its understanding and focus on human aspects and effects of water quality it's been a very productive and a very valuable collaboration that neither agency could fully support. So it's a great, effective and efficient use of agency resources. And for us analytical chemists, I wanted to mention that target and non-target methods should be viewed complementary and not substitutional. And I've heard this from other practitioners of non-target analysis that's been so popular recently, that these are to complement and augment targeted method results. There's not going to be a universal analytical technique that solves everything. But it should be pointed out, this non-targeted analysis based, as I call it, metabolomics approach provides insight to categories of contaminant behavior, even if we can't immediately identify those contaminants. That pattern similarities point to reactivity and potentially or behavioral similarities. And this may add some links between what we observe between chemical composition and concentration from targeted data with toxicity and bioassay results. One thing that should be pointed out, regardless of whether it's targeted or non-targeted, that we're finding, and it's pretty well known, is that, but particularly relevant to non-target, is that sample complexity poses some well-known challenges. We need better and more statistical tools to sift out and identify those right contaminants. And that is an area of intense focus within the non-target community. And the ability to see everything at trace concentrations has had us complete or rethink contamination control, both in the lab and in the field. So blank analysis, your QC load goes up tremendously. So I think I showed this other slide at the very beginning, but again, I want to acknowledge all my collaborators and colleagues who've been producing this work, because without it, I wouldn't have near as much to talk about. And if you have questions, I'd be happy to answer them. My email is shown, so if you're interested in some of the specific reprints, I can make sure those get to you. And at this point, I'd be happy to take questions.
Thanks for a wonderful talk, Ed. I did have a couple questions.
Sure.
Some other ones. So first off, did you mention that when you were looking at your summed concentrations, it's up and downstream of the thing where it wasn't too different? Do you think that's mostly driven by a few chemicals that are present in so much higher concentrations, such as the sucralose? Because when you showed your chart, the sucralose was in the 20,000 range.
That's true. I deleted a couple of other slides that I pointed that that sucralose was high. So it's always a challenge. We can always say, this is what we see, and sometimes that's why I showed the sulfamethoxazole, sucralose, and carbamazepine. There's an order of magnitude difference between sucralose and carbamazepine, and order of magnitude difference lowers the sulfamethoxazole, but the patterns are the same. I don't have them in this particular presentation as added slides, but I have some other plots of the other targeted pharmaceuticals. The patterns are the same, and I'd say that's what's most important. But because I have a suspicion, I can't answer this with any greater data information, any greater informed knowledge that the sucralose is relatively is less important in the glucocorticoid assay, for example. I have a feeling other contaminants might be more important, and some of them may not have been measured by our targeted method, which is why we wanted to start looking at least at the non-targeted analysis data. And we're definitely pulling candidates out there, but this data is yet to be fully. I'm working on it in the publication process. So
okay,
that's why I retired, so I could find some time to do that and some of the many of the other things that I've been doing.
Okay, the other question, two other questions I had.
Sure.
In terms of, you mentioned the fexofenoxidine.
Phenylphenidaene, yeah, Allegra.
That you didn't see it in targeted at times, but you were seeing it in non-targeted.
Well, I was seeing a response, and that's just simply we were using a triple quadrupole, using multiple transitions from a precursor product, and there just might have been interferences in a low resolution quadrupole technique that we clear out in a sense using a high resolution technique.
No, two different instruments, so two different detection limits. And finally, I was going to ask, you mentioned the 8 or 9 PFAs. Were you looking for all the analogs? Because I know there's like thousands of different analogs when you did.
Right. No,
that part of the untargeted work.
And that will be part of the untargeted. That's work Mark Mills has done. For the PFAS we did, that was done by Scott Boone using a triple quad method and looking at approximately, I want to say 19, the 19 primary PFAS molecules that are also part of EPA 537 method, EPA method 537.1 that Jody Shoemaker's developed. Those were targeted PFAS method. Mark Strinner, we've been collaborating a bit with, at some point I'm hoping we'll do some of the PFAS work on some of the POSIS extracts, but that, I don't know, he is pretty overloaded at the moment, and EPA has been moving mountains trying to come up with more information regarding PFAS, and he's developing he's developed non-target methods, as have several others. But I'm not, that's just what we can measure, again, using a triple quad method, similar to 537.
Okay, I think that's about it for questions, and I think about it for time. I want to thank Ed again for coming on and giving us this webinar, and wish him all the best. And with that, I'm going to end this presentation.
All right. Take care, Brian. It was good talking.